Chapter 4, Section 7. We're introducing coordinate proof. Our objective is to position figures in a coordinate plane for use in coordinate proofs and to prove geometric concepts by using coordinate proofs. So go ahead and pause the video, take a look at your agenda, find the DOK chart, and use the depth of knowledge words to write an essential question. Your first strategy for positioning figures on a coordinate plane is to use the origin as a vertex, and I'm going to say focus on this one because this is the one that we use almost all the time. Or you can center the figure at the origin. So if this is my plane and I have a box or a square, I'm going to put the center there. This one means that if I have a coordinate plane, then I'm going to insert my square so that it has a vertex at the coordinate. And then it stays in quadrant 1. So if you remember, this is 1, this is 2, this is 3, and this is 4. The other suggestions are to center one of the sides of the figure at the origin. So if this is my coordinate plane, then I'm putting the center of one of the sides of my square there. There's my center on all of them. Or it says that you can use one or both of the axes as the side of the figure. So this is similar to that one because it's using both of the axes. If I have a shape like a triangle, then I'm only going to be able to use one of the axes. Unless it's a right triangle, then I'll be able to use both. So we're going to put figures on a coordinate plane, and these are our hints in order to be able to solve problems when we have that option. Here's your first task. You need to position a right triangle with a leg length of 2 and 4 units in the coordinate plane. And then here's your hint. Use the origin as the vertex of the right triangle. So the origin is the center of your coordinate plane, and we're going to use that for our vertex of the right triangle. So here's my coordinate plane. Your vertical axis is your y-axis, your horizontal axis is your x. I'm going to draw in my right triangle with a side length of 2 and 4 units. And obviously I don't have a real grid here, so my lines may or may not be very accurate. So if this is my grid, I now know that this corner is going to be 0, 0, and that's where my 90-degree angle is. I know that this point is going to be 2, 0, and I know that this point is going to be 0, 4. The reason why we put this on a coordinate grid is so that now we can use the grid in order to help us find any information that we would need. We can use the distance formula to find the distance between all of the points, which would give you the side lengths of your triangle. Sometimes you use the midpoint formula to find the center, or the slope to find the angle. You're going to use these different things to prove triangles congruent, or whatever the question asks of you, really. So here's the proof that you're going to have to do. And they gave you that there's a rectangle ABCD with A at 0, 0. And you'll see that I've already have this graphed for you. B is at 4, 0. C is at 4, 10. And D is at 0, 10. What they want you to do is they want you to prove that the diagonals bisect each other. If I just had this shape with no other information, then I wouldn't have enough information to make this proof. But because it's on a coordinate grid, if they're bisecting each other, then that means that these lines intersect at the center of both diagonals. And because I have it on a grid, I can figure out where that center or that midpoint is. So if I take AC and I plug it into the midpoint formula, I'm going to find the midpoint of AC segment, don't forget the sign. That's going to give me, and then my points are here, so that's going to be 0 plus 4 over 2, and then 0 plus 10 over 2, which gives me the 0.25, 2, 5. And you can see that it crosses right there. Now if I were to find the midpoint of the other diagonal, so I've got BD right here, of BD, then that one is going to be 4 plus 0 is 2, or excuse me, over 2, and 0 plus 10 over 2, which also gives me 2, 5. Now, because these these diagonals of this rectangle both cross at the same midpoint, then that means that they are bisecting each other. Here we're asked to position a square with side lengths 4p in a coordinate plane. Another nice thing about coordinate proofs are that you can prove a statement is true for all of something, all right triangles, all rectangles, all squares, without knowing the exact length. So this is kind of a baby step that we're going to do in order to get to that point. So I'm going to start with my grid. And one of our hints was that we need to position our shapes with either the side length or the center or the vertex at 0, 0, so at our origin, and we're going to make sure to do that. So here's my 0, 0 point, and we're talking about a square. So I'm going to draw on my square before I really know what my labels are. And it says the side length is 4p. Well, if this side is 4p, then that means that in order to get to this point, I need to move 0 to the right and left, and then 4p up, because that's what the length of the side is. So this is going to be 0, 4p. And then this point here, I need to move 4p out to the right and then up and down 0. So this is going to be 4p, 0. And then this point out here, I'm going to need to move 4p out to the right and then 4p up. So this is going to be 4p, comma, 4p. Now right now this doesn't mean anything. I'm just naming the coordinates of each vertex so that I can practice doing this later when we do proofs with this. On the next slide, for instance, we're going to do something that's a little more meaningful. So here's our proof. We need to prove that the diagonals are congruent. We have rectangle PQRS, so PQRS, and we're going to stick that on a grid. I don't know what all these rectangles are doing here. So this is going to be my coordinate plane. Vertical axis is my y-axis, horizontal is my x, and I stuck the corner on the origin on purpose. So this point is going to be 0, 0. I don't have any numbers for any of these, so I'm just going to make this distance right here B, and this distance across here, A. So if that's the case, then from here to here, I'm going to go A units to the right and then up 0. You can pick whatever letter you want, it doesn't really matter. I didn't want to pick any of these because those are the names of my vertices. And then if I chose this to be B, then I'm going to go B units up, but 0 units to the right and left, so this is going to be 0, comma B. And then to get to the Q, I'm going to move the same number of units to the right, so A units to the right, and then the same number of units up. So A to the right and B up. Now that I have these general spots, and we want to talk about diagonals, to find the diagonals from here to here and from here to here, we're going to use these variables and the number 0 as our points, and we're going to do the same thing we did on the last one, where we're going to use a distance formula. Oh, you know what? Last one we used midpoint. Alright, well this time we're going to use distance, because we want to prove that the diagonals are congruent, not that they bisect each other. So if I apply the distance formula to segment PR, I'm going to end up having the square root of a squared plus b squared. And if I do the same thing for QS, I'm going to end up having the square root of a squared plus b squared again. So because these two measurements, even though they don't actually have numbers in them and I don't actually know what those numbers are, I know that they're going to be the same no matter what number gets substituted because the variable expressions are the same. So now I know that the diagonals are congruent. PR is congruent to QS. Hopefully this is helpful. If you had a hard time with it, watch the video over again. Things get a little sketchy when they're abstract and we have a lot of variables going on. So once you've finished watching it a second time, if you need to, go ahead and write your summary, and below your summary include any additional questions you may want to ask in class.